Hello everyone. Okay, let's continue the week 4 concepts. Okay, we continue with the free vibration with hysteretic damping. Hysteretic damping, in fact, is another type of damping that there is in most of the structures, and this is due to the internal frictions of the different layers of the material. If we consider a material, it consists of several layers. When this material start to vibrate or start to move due to the friction between these layers, will affect similar to damping on your structure, and after a while your uh, amplitude of the motion will decrease and will vanish. So this is a new type of the damping. Again, we start with a viscous damping to model and find an equivalent model for hysteretic damping. For this purpose, if we assume in a system with viscous damping and equation, force equation kx plus cx dot is, and consider that xt is a sinusoidal function or is a harmonic of sine function with uppercase x amplitude and omega frequency, xt will be equal to uppercase x sine omega t, and f is equal to, when you substitute here, f is equal to k times by xt, which xt substitute from this assumption, and plus c times by x dot, which x dot is the derivative of xt, and it's equal to x times by omega times by cosine omega t. So we can substitute, and also we can use this note that sine squared plus cosine squared is equal to 1. So we can conclude that cosine omega t can be substituted by square root of 1 minus sine omega t squared. And then we can substitute into this relation and find a new term for f, which is equal to k times by x plus minus c omega square root of uppercase x squared minus lowercase x squared, which uppercase x is the amplitude of the lowercase x. So we will use this term to plot the force displacement diagram for a system with viscous damped. I mean, we extract this relation, which is a function of x for f. So now we can plot f for versus x. And if you plot, we can extract this diagram. As you can see, this is a curve or a loop, and the energy dissipated in each cycle is the enclosed area by this curve. If you calculate this, and you can, for the initial assumption for the sinusoidal displacement, you can extract that the energy dissipated is equal to pi omega c uppercase x squared. So this is a relation, and this is a curve for a system with viscous damping. And we can now plot the same diagram for a system with hysteretic damping. From the strength of material, you know that you can plot the stress strain or force displacement diagram, something like this, in a flexible structure, which is a curve for a complete cycle of loading and unloading. Again, in this structure with hysteric damping, if you want to extract the energy dissipated in one complete cycle of loading and unloading, the energy dissipated is equal to, similar to the previous slide, it's equal to the area enclosed by this curve. And you can extract this energy dissipated and compare with previous slide, which was for the viscous damping system. you can compare and conclude that H, which is the hysteresis damping constant, is equal to C times by omega. So we define a new parameter and we call it H, which is the hysteresis damping constant, and it's equal to C times by omega. But from the experimental test, when we do the experimental test, we practically concluded that this H, or the hysteresis damping constant, is not a function of frequency, or it's not dependent on the frequency of the structure. So we need to expand this H and find a new parameter, which using the mathematical equation by considering X in exponential form. As you know, we can consider the response in sine, or a combination of sine and cosine function, or we can consider as exponential term when we have an underdamped motion. So here you can see that the response is equal to uppercase X times by exponential I omega t, which you can expand exponential I omega t and write it in the combination form of sine and cosine function. So if you write X in this form and substitute into the equation for the force F, you can conclude that F is equal to Kx plus C times by X dot, which X dot is in fact I omega times by X. And instead of omega times by C, we can substitute H, and we can rewrite this equation in this form. Now we can define a new parameter beta, which is a dimensionless parameter for damping, and it's equal to H divided by K, and we can write F in this form, K times by 1 plus I beta times by X. And now we can write the energy dissipated as a function of beta, and it's equal to pi K beta X uppercase X squared. Now to find the equivalent damping coefficient, the viscous damping coefficient, we can find the relation, the ratio between the two consecutive amplitude of the motion, xj and x sub j plus 1. And if you simplify the equation, it's approximately equal to 1 plus pi times by beta, which is a constant value. And if you calculate the delta to find the logarithmic decrement, it's approximately again equal to pi beta. Now we can simplify, and using this delta, by using the relation between the psi, which is the damping ratio, and delta, the logarithmic decrement, we can simplify and find an equivalent damping ratio, which is equal to H divided by 2K, or beta divided by 2. And also we can find one equivalent viscous damping constant for the structure, which is equal to H divided by omega, or beta K divided by omega. So we can use this equation and the relation to find an equivalent viscous damping system for a system with hysteresis damping, and we can substitute and find the response for this type of system. So then first step, we need to find an equivalent viscous damping constant, C equivalent, or damping ratio. And then by using this data and the natural frequency, we can extract the equation of motion and solve the equation of motion and find the response for a system with hysteretic damping. Of course, these assumptions and this response is only valid for a harmonic excitation, because in our initial assumption, we assume that the response is a sinusoidal form. So this is only valid for a harmonic excitation. Here you can see we have a flexible structure the force displacement curve for a structure is shown. The structure is modeled as a STF system with equivalent mass 500 kg located at the position where the measurements are made. Describe the response of this structure when a shark imparts a velocity of 20 meters per second to this point on the structure. So we have the initial condition according to the problem description. The initial condition is 20 meters per second. Here, if you look at this curve, this is the force displacement curve. So we can calculate, of course, we can in fact estimate the area enclosed by this curve by counting the number of squares or rectangles, in fact, and then we can calculate the total area enclosed by this curve. So we will have the energy dissipated. We have the initial condition, which initial velocity is 20 meters per second and initial displacement is 0. We have the mass of the structure, which is 500 kg. So we need to find the stiffness of this structure and also the damping ratio, or in fact, the equivalent damping ratio. So as I told you, we can find the energy dissipated in this structure. Here we will have, if you count the number of the squares in this area, it's about 38.5 squares multiplied by the area of each square. Here, if we find the area for each square, it's a square with dimension, this length is 2 millimeter, because here we have we have 10 here, and if you count here, it will be 2, 4, 6, 8, and 10. So the horizontal edge is 2 millimeter, and the vertical edge of each square is 1 times by 10 to the power of 4, or 10,000, or 10 kilonewton. So the dimension is 10 kilonewton, or 10,000 multiplied by 2 millimeter, or 0.002 meters, and times by the number of the square, which is 38.5, and it's approximately 770 Newton meter. This is an estimation for the energy dissipated in one cycle. So now we need to find the stiffness of the structure. This is the force displacement curve. You know that in a structure if you want to consider this structure as a spring, the force displacement relation is equal to F is equal to K times by X. So K is in fact the relation or the ratio of F to X, and we can find K according to this curve, because here the vertical axis is F and the horizontal axis is displacement, or X, in millimeter. So if you find the slope of this curve, which is F divided by X, and for this point, for example, F is 5 times by 10 to the power of 4 divided by 10 millimeter, or it's equal to 0.01. Or also you can use from, for example, this point, which is F is approximately 1 times by 10 to the power of 5, and the displacement X is 20. So you can use this data to find K. So here, as I told you, you can find the stiffness of the structure, which is 5 meganewton per meter. And now we have K. This is the stiffness. We have the energy dissipated from the area enclosed by the curve. Now we can find the H for the system or the hysteresis damping constant, which is the energy dissipated delta E divided by pi k uppercase x squared, which uppercase is the amplitude of the vibration. Here you can see the amplitude of the vibration is 20 millimeter, as you can see, the maximum displacement. So we can substitute, and 20 millimeter, or we should convert it into meter, which is 0.02. The stiffness is calculated in this part. Delta is calculated in the first part, and we can substitute, and finally the H, which is 0.00245. Now easily we can find delta, because delta is equal to pi times by H. Damping ratio is H divided by 2, and the natural frequency, which is equal to a square root of K divided by M. So now we have this data, and we can form the equation of motion for this structure, and it's equal to, in a standard form, it's equal to x double dot plus 2 cosine omega n x dot plus omega n squared x is equal to 0, and there is no external force, so in the right hand side it's equal to 0. The initial condition according to the problem description, the displacement at t is equal to 0 is 0, but the velocity at t is equal to 0 is 20 meters per second. So now the next step, we need to solve this equation. In fact, this is the equivalent equation of motion for a system with hysteresis damping, but in equivalent form, which we consider the hysteresis damping as a viscous damping. And here you can see in the equation of motion, we have damping ratio. And again, I should mention that this equation valid only for the harmonic excitation or harmonic motion. Okay, so the next step, we need to solve this equation according to the initial conditions. Okay, similar to the previous section, we can solve this equation. This is an ODE from order 2. Easily we can find the roots of the characteristic equations. The characteristic equations is alpha squared plus the coefficient of x dot times by alpha plus the coefficient of x. The roots are complex conjugates, and we can find the xt, or the homogeneous response, which is the exponential of the real part times by t, multiplied by c1 cosine homogeneous, the imaginary part times by t, plus c2 times by sine imaginary part times by t. So this is the homogeneous response, and we have two constants, and we need to find these two constants, which are extracted from the initial condition. At t is equal to 0, it must be equal to 0. So we substitute t is equal to 0. It will be exponential of 0, which is 1, cosine of 0, which is 1, and sine of 0, which is 0. So it will be c1 is equal to 0, and we can conclude, so c1 must be 0 for the to satisfy the first initial condition. The second initial condition, the velocity at t is equal to 0 must be equal to 20 meters per second. So we need to find the derivative of x with respect to time, and the derivative of x with respect to time is the derivative of exponential term times by this parenthesis plus the derivative of this parenthesis multiplied by the exponential term. And if you calculate this derivative and substitute t is equal to 0, you can find that c2 is equal to 0.2. Now we have two constant coefficients, and we can substitute, and finally the response of this system, which is 0.2 times by exponential of minus 0.122t times by sine 100t. This is the response of the system, and in fact this is an estimation of the response for that system by assuming that we have a harmonic motion. And also we can use the formula. As I told you, I suggest you always to solve the equation directly using the common procedure, and do not You don't need to memorize any equation, okay? But you also can use this equation and you can substitute and find the response. Okay, any question from this example? Is it clear?
Yes, it's clear.
Okay. Okay, next example, we have a built-up cantilever beam having a bending stiffness of 200 Newton per meter, supports a mass of 2 kilogram at its free end. The mass is displaced initially by 30 millimeter and released. If the amplitude is found to be 20 millimeter after 100 cycles of motion, estimate the hysteresis damping constant beta of the beam. So here, in this case, delta is equal to, we can obtain delta similar to the viscous damping system because we have a harmonic motion. So we can find the logarithmic decrement, which is equal to 0.00405. And it's equal to, because in 100 cycles, the amplitude from 30 millimeter, the initial amplitude was 30 millimeter, and now it's 20 millimeter after 100 cycles. So delta can be calculated, and now we can find beta, which is delta divided by pi. The last concept for this week is the stability of the systems. In stability, when you deal with a dynamic system and you want to study the stability of a structure, there are a lot of different definitions when you deal with different structures. For example, in a control, we have different definitions. In static, when you deal with a buckling, for example, buckling phenomena, the stability will have a different definitions. But here in dynamics or in vibration, we have another definition for stability, but generally maybe the pair of the definitions are different, but in terms of the mathematical point of view, all of them have the same definitions and all of them are the same. Here we define the stability for a system with vibrating motion. If we assume that xt is the response of the free vibration, and when the limit of xt for t when goes to the infinity is equal to 0, we can conclude that the system is asymptotically stable. By using this criteria, we can define the stable and unstable for the system. So when a system is considered unstable, that in this system, xt grows without bound and approaches infinity as time approaches infinity. So for an unstable system, the amplitude of the response will increase without any bound by time. And for a stable system, when the amplitude of the response it will remain the same. I mean, it's the amplitude of xt neither decays nor grows and will remain the same. So this system will called a stable system. There are some conclusions. In fact, these conclusions are extracted from previous section when we discussed the effect of the roots of characteristic equation on the behavior of the system. We discussed these results, but here again we review them. The signs of the coefficient of the characteristic equation determine the behavior of a system. As you saw in the previous chapter, when we plotted the results and the effects of the position of the roots in S-plane on the behavior of the structures, we concluded that when the roots of the characteristic equations have negative real parts, the system is asymptotically stable. It means that the amplitude of the system, amplitude of the response, decreases to zero after a while. But when the roots of the characteristic equations are they have real positive parts, they are unstable, and the amplitude of the response increases without any bound. And finally, if the real parts of the roots in the characteristic equation was zero, the system was stable. I mean, the amplitude remains the same without any change. In an unstable system, the free vibration response may grow without bound, with no oscillations. We call it divergent instability. Or it may grow without bound, but this time it will have oscillation, which we call it flutter instability. And the second case also are known as the self-excited vibration. This case is related for some specific systems. When you derive the equation of motion, you see that the coefficient of x dot, or the coefficient of velocity into the equation of motion, has a negative sign. In the previous equations, in the previous systems, when we extract the equation of motion, always you see that the coefficient of damping is a positive value, but sometimes there is no damping. But when you extract the equation of motion, you will see that sometimes the response depends on the velocity, but there is no viscous damping. But due to the physical behavior and some other reasons, the response is depends on the velocity of the motion, but this effect will be appear with a negative sign, and that negative sign will affect as uh, a new term, which instead of decreasing the amplitude of the response will increase the amplitude of the response, and it's called the self-excited vibration. The next conclusion is for a linear model of an asymptotically stable system. For all of the initial conditions, always the response will be zero, and it will be bounded. I mean, we cannot find any initial condition for which the response of this system approaches infinity. But on the other hand, for a system with unstable system and with unstable behavior, maybe we can find some initial condition which, for this specific initial condition, the response can be can be finite, and the response can approach to zero. So for the system with asymptotically stable behavior, always the response is bounded and the response will achieve to zero. But for an unstable system, the response is usually the amplitude of the response is usually increasing by the time without any bound, but we can find some initial condition that in this initial condition, and according to this initial condition, maybe the response can decrease, the amplitude of the response can decrease, and the response approach to zero after a while. The stability of the system also can explain in terms of energy. This method is usually used in control especially, and we call it Lyapunov stability criterion. It's very useful method when you want to control a structure, and you can define according to this scheme, you can define a new definition for the stability, and we can say that a system is asymptotically stable or unstable if its energy decreases, remains constant, or increases respectively. So you can see again for a system, for the stability of a system, we can use this definition. But when you use the mathematical equation to define this stability, again, we will extract the same relations, or at least we can extract the same behavior for the structure. And finally, stability of a system can also be investigated based on how sensitive the response or motion is to small perturbations. These perturbations or variations can be applied to the mass, to the damping, and to the stiffness of the system. And you can investigate the behavior of the structure versus applying a small perturbation to your system. So if your system has a very huge variation in the response when you apply a small perturbation to the, for example, to the damping constant, so you can conclude that your damping is not stable, or your damping will create instability on your structure. So you can examine your behavior by using the perturbation method as well. Here you can see different diagrams for different structures. Case A is a stable system. As you can see, the amplitude of the response remains the same by time. Case B is an asymptotically stable system. You can see after a while, the response vanishes and the amplitude is 0. Case C is unstable system, but this is a bit divergent instability. As you can see, there is no vibrating motion. And finally, case D is again unstable, but this is called a flutter instability, because we have vibrating motion, but the amplitude is increasing by time. So these are the summary for the stability behavior in the response of the structures. Okay, here we have one example, and with this example we can wrap up this session. Any questions so far?
No, sir.
Okay. Consider a uniform rigid bar of mass m and length L, pivoted at one end and connected symmetrically by two springs at the other end, as shown in this figure. You can see, assuming that the springs are unstretched when the bar is vertical, derive the equation of motion of the system for a small angular displacement theta of the bar about the pivot point, and investigate the stability behavior of the system. So first we need to extract the equation of motion. For this purpose, in this type of structure, when we deal with a rigid body, because you know that this bar is a rigid body, I suggest you to use the energy methods similar to the dynamics, and you can solve and use the energy methods to extract the equation of motion and solve the equation of motion for the natural frequency. So for this purpose, we need to form the kinetic energy and potential energy. Here we have one rigid body. So in the kinetic energy, we only have one term, which is for a rigid body. Here, this rigid body is rotating about a fixed point here at point O. So you can write the kinetic energy for this rigid body in two different ways. I mean, you can write about point O, because here this is a fixed point and this is a pure rotational motion. You can easily write the kinetic energy is equal to the half times by the mass moment of inertia about point O, which is the fixed point of rotation, times by theta dot squared, which theta dot is the angular velocity of the rigid body. Or you can write the kinetic energy about the mass center here in this time, if you want to write the kinetic energy, you will have half times by mass moment of inertia about the mass center this time, not point O, times by theta dot squared. And in addition to this term, we have the linear velocity, because this point G is moving with a velocity of, if we assume that this rigid body has angular velocity theta dot about O, so the velocity of point G is L over 2 times by theta dot. So it's equal to the half times by the mass of the bar, which is M, times by the Vg, which is L over 2 times by theta dot squared. So definitely the best option is writing the kinetic energy about the fixed point, because it's easier. We will have half IO theta dot squared. The potential energy, here we have two springs, as you can see. So easily you can write half times by kx squared, and we have two springs. So it will multiply by 2. But the displacement of this point A is equal to, if we assume that the degree of freedom is theta, because we assume that the angular velocity is theta dot, so it will be theta. So the displacement of point A is equal to L, the length, times by theta. Or here, in fact, it's equal to L times by sine theta, but you can substitute the sine theta, because according to the problem description, here in assuming that the spring are unstretched when the bar is vertical, here for a small angular displacement theta, so we can substitute, instead of sine theta, we can substitute theta. So the displacement of point A is L times by theta. And this is the potential energy in these two springs. As you can see, 2 multiplied by these 2 is because we have two springs, multiplied by half K L sine theta, or L theta squared. And here you can see we considered the gravitational potential energy in the total potential energy. And this is because the weight of this body did not create any initial deflection in these two springs. So we must consider the weight in our equation. Even when you are using the Newton's second law, definitely you should plot the free body diagram and write the moment equation, for example, about this point O. Even in Newton's second law, you need to consider this weight in your equation of motion. So here, the potential energy will include the gravitational potential energy. And if we assume that, for example, this is the datum level, you can extract that the final position is mgl over 2 times by 1 minus cosine theta. Because, for example, if we assume this is the position of point G, and this is the L over 2, okay? So this is the initial position. When it's going to the position theta, for example, here, and this angle is theta, you need to calculate the change in the length of this line, which is this distance. And this distance is equal to L over 2 times by 1 minus cosine theta. Okay, because this length is L over 2, and this length is L over 2 times by cosine theta. Okay, L over 2 cosine theta. So this is called, for example, H. H is equal to L over 2 minus L over 2 cosine theta, or L over 2 times by 1 minus cosine theta. Here you can see this is L over 2 times by 1 minus cosine theta, and mg, which is the weight of the rigid body. So the next step, as I told you, again, 1 minus cosine theta can be substituted by theta squared divided by 2 from the Taylor expansion. Because theta is small, so we can substitute the sine and cosine by their Taylor expansions. and simplify because theta is small, and we can in fact linearize the equation of motion. The next step, we need to find the derivative of t plus u because this is a conservative system. So the derivative of t plus u with respect to time must be equal to 0. And if you've calculated the derivative of these terms, you can easily find the equation of motion. You know that to find the derivatives here, half times by IO are constant, and the derivative of theta dot squared, which is 2 times by theta dot times by theta double dot. And here for this term again, K and L are constants. So we will have only theta squared, the derivative of theta squared, which is 2 times by theta times by theta dot. And theta dot will be comes out from the parentheses, and the terms into the parentheses is the equation of motion, and it must be equal to 0. So the natural frequency for this system is the square root of the coefficient of theta divided by the coefficient of theta double dot, which is the natural frequency. And now we can discuss the stability of the system. Any question? Is it clear?
Yes, sir.
Okay, to here, as I told you, this is the natural frequency. And now we can discuss the behavior of the structure according to the sign of this term, 12k L squared minus 3mgl. And we can plot the response for different cases. Here you can see if this term was positive, the behavior is stable. So the structure will stable. In fact, in this structure is naturally unstable, but you can see by changing some initial condition and by changing the value of k, you can control the motion and you can extract a stable response. But for the two other cases, when the term is 0 or is negative, you can see we have some unstable behavior because the amplitude of the response increases without any bound, as you can see in two other cases. So these are the behavior of the structure, and you can see for the positive value, so it will be stable, and for other cases it will be unstable. Okay, any questions? If you don't have any question, we can wrap up this session, and after a break we can start the tutorial session.
Okay, sir.
Okay, thank you.
Thank you.